Today we're doing 6.3. We're starting 6.3, and it's really important that we understand how square roots work, how cube roots, fourth root, fifth root, and sixth root work. So the first thing we're going to do, we're going to look at these perfect cube values. So 1 to the third is 1, 2 to the third is 8, then you got 27, 64, and then 125. You guys with me on that? Okay, so whenever you do 1 to a power, every single time, what did you get? 1. Okay, so for all of these, you should have 1. And then if 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth, 32, and then 2 to the sixth, because you're just multiplying by 2 each time. Okay, when you do 3 to the fourth, that's the same thing as 9 times 9, because what's 3 times 3? 9. Okay, so that's how we would know that's 81. This is 16 times 16, so you might not necessarily know that one. And then 25 times 25, 625. So what we need to associate with these perfect numbers is that when you take the cube root of 1, the reason why it's equal to 1 is because it's 1 to the third power. Okay, the cube root of 8 is 2 because that's 2 to the third power. Okay, and so these numbers that you see underneath the radical, we're going to start simplifying those numbers because we're going to expand from square roots into cube roots, fourth, fifth, and sixth. So we've mostly been working with square roots. We did a little bit with perfect cubes when we were factoring. Okay, but anytime you're taking the root of 1, no matter what your root is, you're always going to get 1. Okay, now depending on what, this is called your index number, the 4, we're going to learn about that in a moment. When you're taking the cube root of 8, you get 2. When you're taking the fourth root of 16, you get 2. Okay, so the answer can be the same for 2 different radicands and 2 different roots. Now, when we do this, we're going to be making our factor trees. So for some of the numbers that are smaller, I think it's beneficial for you to know those off the top of your head, like the cube root of 8, the fourth root of 16. That's going to make it a little bit easier for you. But we're also going to be using our factor trees and what we know about how roots work. Okay, so that's what we're going to be talking about today. So we should have got 243, 1024, and 3025. And then here we had 729, 4096, and 15625. Okay, like this number 5 to the 6, we're not going to be doing a lot of work with that. Okay, but these fifth roots, it is helpful to recognize those. Is 4, and then the sixth root is 729 is 3. All right, so we're just doing our roots now. The fifth root of 243, the fifth root of 1024, the fifth root of 325. All right, so the index of a radical. What is the index of a radical? That is going to be the root. And in general terms, if you have the nth root of x, we say that the index is the root n. Okay, the index is the root n. It says, what does it mean if there's no index? Really what that means is, what if you can't see the index? So if it's like this, what's your index number there? 2 because it's the what? It's the square root, okay? So what we're not going to do is we're not going to start writing the 2's there now, okay? That is not a thing. So the square root is going to look the exact same. Just know if you don't see a number that it's going to be 2. Okay, so this chart that you have here, the numbers and the types of real roots, that is what you're going to use if you are solving. We're mostly going to be doing simplifying today. In fact, I don't think I had you guys write up your objective. But our main purpose today is going to be simplifying radical expressions. Okay, we're going to simplify radical expressions. But to do that properly, we have to understand how the roots work. Okay, so if you have an odd index, that means you're taking the cube root or the fifth root of something, then you have one real root. So if you were to take the cube root of 8, it would just be 2. If you were to take the cube root of negative 8, it would be negative 2. So whenever you have something odd, it's okay if it's a negative because odd numbers, when you have an odd amount of negative numbers, it multiplies to a negative. Okay? So we all know the square root is 9. Do you guys know why? We all know the square root of 9. What is the square root of 9? 3. Do we know why the square root of 9 is 3? Yep. So 3 squared. This is a root and a power. They are inverses. Inverses undo each other. Okay? So if you have negative 2 to the third power, you take the cube root of that, you're left with negative 2. That's how it works with the negative 8. Okay? The cube root of negative 8 is negative 2. Mm-hmm.
I have 2 questions.
Yeah.
Are you able to have one first?
No, you won't. You won't have that. Because you need like a group.
Alright. And then also are you able to have
No. So if you have a negative power, which is actually what we're doing tomorrow, we're going to put it over 1. Yeah, so you can't have any negative roots. Yep. Yeah. All right, and then the even index is going to have 2 cases, because if you have a positive number underneath, that's the radicand, that results in a plus or minus. Okay, and that's going to happen when you're solving. So they gave you the fourth roots of 16. If you were to take the fourth root, it would be plus or minus 2. Okay, and that's what we've been practicing with our square roots. If you have a negative radicand, notice it says 0 real roots. And that's because the roots aren't going to be real, they're going to be imaginary. Okay, and if it says to find the real roots, which we're going to practice, then you don't have to find the imaginary. Okay, and then the last one is the radicand of 0. So we've done this as well. When you're taking the cube root of 0, what is it? 0. And it's the same premise. 0 to the third power is 0. So when you take the cube root, they undo one another. Okay, so before we start simplifying, we are going to start by solving. So this says find all the real roots. So if it's imaginary, you are not going to have to write that out. And we're going to practice solving for the first example. So if it says find the 6 roots of 64, they are asking you to solve this equation for x. So we're going to take the 6th root of each side. And then we can use our chart for this. Is the 6th root of 64 something in our chart? Yep, it says 2. So because we're taking an even root, the roots are going to be plus or minus 2. So if you have a positive radicand, you're going to have the plus or minus there if you're solving. Okay, the next one is the cube roots of 216. So it will be x to the third equals negative 216. Okay, that is not in our chart, so we're going to practice the factor tree method so that we can refresh ourselves with that. And because it is a negative, we know our answer is going to be negative here. Okay, so we're just going to do the factor tree for 216. So whenever you're doing a factor tree, you want the prime factors. So what are good numbers to see if they go into 216? I wouldn't do 6 was not prime. Yeah, 2 or 3. They both go in there. I like to start with 2 because if I'm doing this without a calculator, it's easier to cut it in half, right? Okay, so we are going to be doing this without a calculator. So what's half of 216? 108. And then we're going to keep going. So half of 108. Yep. And then once you get to 27, okay, then 2 doesn't go into 27, so you're going to try 3. So 3 and 9, and then that breaks it down to 3 and 3. Okay, so now that you're doing that, before we were doing it with the square roots, and how many did we need in order to come outside? We needed 2. So now we have to have a group of 3. So if you have 3 2s, the 2 comes on the outside. If you have 3 3s, the 3 comes on the outside, and what do you do with them? Multiply. Okay, so 2 times 3 is going to be, nope, that's adding. Yep, negative 6. Good. Okay, so x equals negative 6. Okay, and then we have the 4th roots of negative 1024. Okay, so when you take the 4th root, it's an even root, it's a negative number. Because the direction says find all of the real roots, your answer is just going to be that there's no real solution. We can use the symbol for that. It's because it's an even root. Yes, if it was an odd root, then we would factor tree it. And if you could find imaginary, we would factor tree it. Okay, but for this, there's no real solution, and that's because you can't take the even root of a negative. Okay, that produces imaginary solutions. Okay, so we are going to be applying properties of radicals now to different roots. So one of them that we use over and over again is splitting up with multiplication. Notice here it says for the values a is greater than 0 and b is greater than 0, which means they're both what? What does it mean if something's greater than 0? Positive. Good. So these are your positive values. Okay, and the reason why that exists is because if you had 2 negatives, then you'd multiply them together and it would be a positive, but that can't happen because the negatives are going to produce imaginary answers if you have an even root. Okay, so that's why you have to be careful with those. Okay, and then we've been doing simplifications like that for a while, right? If you have the square root of 12, what's the perfect square in 12? Yep, so we write it as root 4 times root 3. You don't have to write this down. I just want to remind you that we've been doing this for a while. So then you simplify it to 2 root 3. Today we're going to do this, but we're going to expand it to cube roots, 4th roots, 5th roots. Okay? All right, so if you are dividing, you can use this as well. Okay, and if you are dividing, that is where you end up with the square root on the thing. So you can put that again. You're cold? Okay. I'm looking down for like a full minute. Okay, and then once you have the end root, okay, of the top and the bottom, then you are going to split this up. And if this is a radical, do you guys remember what it's called, the process that we do? We are going to multiply by something. That's not what it's called. We are going to multiply with a conjugate for this one. What do we do to the denominator? We are going to multiply by something, yes. What's it called? What's that called? What is it? No? Well, it does start with an R and an A. All right. It is called rationalizing, and then let's talk about why. So maybe that can help us remember. You're rationalizing the denominator. So when you have square roots that can't be simplified, they're irrational numbers, right? Irrational. So what you do is you multiply, so it's a rational number, like a whole number. Okay, so that's why it's called rationalizing, because you're changing the number from irrational to rational. Okay, so we've done that with something like this, 2 over root 5. Okay, and so we'd multiply the top and the bottom by root 5. And you guys are really good at patterns, right? So a lot of you have gotten really good at knowing, okay, root 5 times root 5 is going to be 5. Make sure that we understand the reason why that happens is because when you multiply those together, it's the square root of 5 squared. The square root undoes the power of 2. And the reason why we want to understand that is because we are no longer going to just be working with square roots. Now we're going to be working with cube roots, fourth roots, fifth roots, and so on. Okay, so that changes the thing a little bit. All right, so we're going to simplify. We're going to start with a square root, okay? So it says simplify each expression, assume all variables are positive. Your book doesn't necessarily do this, so if you look in the book for examples, just know that they're going to put like some plus or minuses in there or absolute value. We're not going to worry about that right now, okay? We're just going to simplify. We're going to assume everything is positive. So we're going to do 81 times x to the 12. Okay, and then what we can do is we can split this up into the square root of 81 times the square root of x to the 12. Okay, so 81, we know that. What's the square root of 81? 9. Okay, for the rest of it, I'm going to show you some visuals. This isn't something you're going to have to write out every time, but I want you to have this for your notes. So we're going to make sure we understand what the index number is. So this is your index. It's 2 because you can't see it, so it's a square root. Okay, and that lets you know how many groups you have to have, how many factors you have to have in order for it to come out. So 9 squared is 81, which is why we take out the 9. For x to the 12th, okay, I want you guys to visualize this. If you have x to the 12th, you have 12 x's multiplied together, right? Let's write those out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, lots of x's there. Okay, and we're going to use that same concept. Okay, so if the index is 2, you need a group of 2 in order for those to come out. Okay, so we're going to circle groups of 2, and anytime there's a group of 2, we're just going to take that out. Okay? Okay, so if you have a group of 2 x's, how many come out? Well, yeah, altogether, yeah. Yes, you will have 6. So it's going to happen once, twice, 3 times, 4 times, 5 times, 6 times. So when you multiply all those together, you're going to have 9x to the 6, okay? So I want you to have that visual so you understand why it works that way. A shortcut that we're going to use is we can just ask ourselves, how many times does the index go into the exponent? Okay, or you can just divide the exponent by the index. So 12 divided by 2 is 6. So you can do it like that. Okay? All right, let's try this one. Do you think you can do that well without me? Okay. Don't tell me out loud, just do it on your paper. Okay, so let's do the x part first. So we just learned that you can take your index number, right, and you can just divide. 12 divided by 4 is going to be x to the third. Okay, so 4 goes into 12 3 times, so that's going to be what you have here. Now for 81, you can do your factor tree, and 81 we know is 9 times 9, and we know that breaks up into 3 and 3 and 3 and 3. So what the 4 through to 81 is equivalent to is the 4 through to 3 to the 4th, right? So what happens when you take the 4 through to 3 to the 4th? It cancels out and you're left with 3. Okay, so your final answer is 3x cubed. All right, now both of those, they had such nice, beautiful answers, but it doesn't always work out that you're going to get a whole number, right? Well, think about the root 12, right? We had something on the outside of the radical and something on the inside. So we know that can't always be that simple, right? Sometimes we're going to have some leftovers. So we're going to do the cube root of x to the 8th. Okay, and then feel free to do that if you feel like you know how to do that without me. I'm good with you trying some things. Okay, so your index is 3. If you're still feeling a little shaky, then I do encourage you to write this out visually so you can see what's happening. You know x to the 8th just means that you have 8 factors of x, right? 1, 2, 3, 4, 5, 6, 7, 8. Now, your index is 3, so you need a group of 3 in order to take it out of the radical, okay? Oh, and I already did something that I don't want to do. It's the cube root, so we're going to keep the cube root. Don't forget your indexes. Okay, so how many groups of 3 do I have here? I have one group of 3 here, so I take out an x. I have another group of 3 here, so I take out an x. But I can't take that out, right? Okay, so the x squared goes on the outside, but then what is left inside of the cube root? X squared. Okay, so an x squared comes out and an x squared stays in, and this is your final answer. Okay, another way you can think of this is you can say 3 goes into 8 how many times? 2 with how many left over? 2, because 3 times 2 is 6, 8 minus 6 is 2. Yeah, yep, it is with the exponents. Yep. Okay, let's try this one. Yeah, make sure you put that in there. Is that what you, yeah, I usually like to do a little space. Okay, so let's do the 4 through to 32. Okay, so as you get better at this, some of you are going to develop different strategies with this. You can absolutely do your factor tree. So when you do the factor tree, you're going to keep cutting it in half. So why don't you finish that? All right, so how many 2's did you end up with here? 5. So some of you are going to know right away that 32 is 2 to the 5th, and that's fine. And then anytime you have a group of 4 this time, because that's your index, that means a 2 can come out. So a 2 is going to come on the outside, but there's also a 2 left on the inside, so it's 2, 4 through to 2. Okay, you can also think of it like this, and this is really what's happening. This is the same thing as the 4 through to 32 equals the 4 through to 16 times the 4 through to 2. Because 16 is a perfect 4th root, and if you have 2 to the 4th, what happens there? They cancel. So that's how you end up with that. Okay, and then, like I said, some of you might recognize right away, oh, 32 is 2 to the 5th. So you can also think of it as, okay, 4 goes into 5, how many times? 2 with 1 left over. Okay, so there are 3 different ways that you might visualize that, and you're going to find what works best for you. Okay? All right, let's try this one. Okay, let's try 128 AB to the 5th. Okay, so why don't you guys start with just the cube root of 128, and I want you to simplify that. Okay, start with the cube root of 128, and then just simplify that. You need your factor tree, and then move on to the variables. How do our factor trees go for this? And again, when you start to notice things like 32 is 2 to the 5th, if you want to make your just 5 2's from there, that's fine. Right? Because don't you know 32 is 2 to the 5th? And then anytime there's a group of 3, 1 comes out. So there's one group of 3, so a 2 is going to come out. There's another group of 3, so another 2 comes out. And then how many 2's are left inside? 1. Okay, so you have 4 cube root of 2 just for the number alone, okay? So what I do when I have that is I'll put the 4 here, I'll leave some space, and then I'll do the cube root of 2, and then I'll go to my variables. So there has to be 3 of them in order for you to take it out. So how many A's are there? 1. So if there's just 1, it can't come out, it has to stay inside. So the A stays inside. Okay, but for the B's, 3 goes into 5, how many times? 1 time, and then how many would be left over? 2. So this is your final answer. 4b cube root of 2ab squared. Okay, so some of these answers are not necessarily pretty or what we're used to seeing, okay, but that's okay. So this is what I want you to focus on is those skills and knowing, okay, if there's a group of 3, that's what comes out based on what the index is. All right, and then this one, we are going to take the square root of 3x to the 5th y. Sorry, I made a very long square root. Oh, that reminds me. When you are writing your answer, don't get lazy with your square root. If something's inside the square root, okay, put a roof over its head. Don't stop short. That means something different. Okay? All right, so for F, we have this multiplication here. When you're multiplying, you can create one big radical, and then you can simplify. So if you're multiplying them together, we can multiply 3 times 8, which is 24. And then when you're multiplying, what do you do with the exponents? You add them together. Okay, and then so this is 1 plus 6, so it'll be y to the 7th. Okay, and then I want you guys to simplify it from there. And with numbers like 24, you can do your factor tree, or some of you are just going to know right away it's root 4 times root 6, right? Okay, so that should be 2 root 6. And then from there, we can go to our variables. So our index, if it's a square root, is 2. 2 goes into 10, 5 times. Nothing left over. Okay, 2 goes into 7 how many times? 3 with how many left over? 1. And I'm going to rewrite that because I don't like the way that it's scrunched together. Okay, and then square root of 6y. Okay, we're going to do more of the division tomorrow, but I'm going to give you a sneak peek just in case you want to do more on your worksheet that's required today. Okay, so you have the square root of 16x over x squared. Earlier today we talked about if you have a fraction, you can split this up into the square root of the numerator over the square root of the denominator. Now you are going to want to simplify where you can. So we're going to break it up into the square root of the top over the square root of the bottom. What can we simplify it in the numerator? Yeah, what's the square root of 16? 4, and then the square root of x squared, x. Okay, and then we have root 7 over root 7. Oh, sorry, because we're rationalizing. You guys with me on that? Okay, so when you do that, the square root of 7 times the square root of 7 is how you get 7. And then the top is just 4x root 7. Okay, I really don't want you to do any of them tonight that have more than the square root, okay, because that can be a little more complicated. And I'm going to go over that with you tomorrow so that your head doesn't explode today, because I know that we cut a lot. Okay,